The last talk for today, and unfortunately it means we are coming toward the end of FOSDEM. So how many of you have been to FOSDEM PG Day, which happened on Friday? Awesome. So if you haven't heard before, we every year, just before FOSDEM, we organize FOSDEM PG Day, one day full of Postgres, if this is not enough for you. And then just visit fosdempgday.org for more details. So we will be here again next year. So the final talk of today is from Ilya, one of our most famous speakers in the community.
Thank you, Devram.
And then, so he's going to speak about the latest evolution of Linux IO stack, explained for the database people, not hackers.
Yeah, thank you, Devram. Hello, everyone. That's the last talk. My congratulations. You pretty much survived this, which is a good sign, probably. The bad side that as the last talk, after almost 3-day marathon, it would be about boring Linux things. But I tried to do that, not that boring, probably. And, well, the main problem with such talks could be that you need to cover too many things, like you need to explain how databases works, how Postgres works, for example, then how Linux works, and then how it comes together. So I try to solve this not easy task. Let's go. So why we talk? First of all, Linux is quite important for the databases. I would say today is actually the default operating system for database use. For a long time, it was not like that. Solaris, HPUX, sometimes Windows, many operating systems are used for databases. Now, actually, like it works usually in open source world. Many even commercial database companies investing in Linux to achieve a better performance for their database. And Postgres, regret to say, maybe for FreeBSD project or from OpenBSD project, now somehow aimed just to improve performance on Linux. Not because those operating systems are worse, but because, well, Linux is what people want to run Postgres. And then the central thing for database workload is fast I/O, because sometimes we run into CPU problems, sometimes we run into this and that. But well, if we have intensive workloads, I/O most likely a common problem which we need to fight with. Well, another problem is then you try to figure out what to do with Linux and its I/O stack to improve your PostgreSQL, MySQL performance, for example, is that you can find some posts on Linux network, some emails into some mailing lists like Postgres hackers or kernel mailing lists, and all the information you can find there is actually made by developers, and the language like they use requires a lot of knowledge, and it's written basically for kernel developers, so not for DBAs. And that task I tried to solve. I tried to get some clue in which direction you need to go for Google to dig for information. And another problem is actually that Linux IO stack recently redeveloped quite intensively, because for a long time it was really lots of problems inside the Linux IO stack, different other problems which kernel developers need to solve. So for a long time it was like nothing happened, and recently during the development cycle of version 3 and version 4 and now version 5, it's really everything changes and whole systems are overhauled, etc. So what we are talking today about, very brief introduction, especially for the first line, how Postgres work with disk, and then slightly historical part, what was in Linux with I/O in old good times of old kernels, and then brief introduction what was new. So basically, maybe you will not have the complete picture after this talk, but at least you need to put down the keywords where to find the information after that. So a very typical database based on these two things, you'll guess that this typical database is typical PostgreSQL database. Works with the kernel space, with the kernel memory, the page cache, the kernel buffer, and it works with the user space, its own shared memory segment. So Linux takes care of this part, and database code takes care on this part. And basically the same idea, this page model is for many years here, and that's very convenient. When you read some information from the disk, you just put the whole page in memory, and then if you change, if you do not change something, it's quite easy. You just like modern in-memory database, you just can read some information, return as select. But when it comes to updates, you can mark some of the pages as dirty pages, and then the I/O problem starts usually. So if you update something, you need to write write-ahead log, and actually at some point you have your information about your recent updates in your write-ahead log, and this memory snapshot is inconsistent comparing to the disk image. So from time to time you need to issue the nightmare of any DBA, especially 10 years ago, the checkpoint, and all the dirty pages are going down to the disk, and that's that I/O problem you usually hit. So basically, if you had only read workload, that's not that bad. Then you have writes. That's probably can be a problem for you. If we're talking about database, because we can talk about full text storage, about file server, for a database there are very specific key features for its workload. Shared memory today, well, could be defined with the prices of RAM. And then I started to perform talks about how to tune Linux for Postgres. I used to say, well, now 32 gigs of memory are cheap. Some people started to laugh because it was quite expensive at that time. Now, actually, I would say that 1 terabyte of memory is not that expensive. So basically, you can have a lot of memory on your database server, and you need to use specific settings. And, well, Linux and database, your favorite database, Postgres, I hope, should adapt to that. So it can be really a lot of data. And then you synchronizing those pages, this huge amount of data travels down and up. So basically, here's the I/O problems. Besides that, there are different things with I/O which can be not that bad, like checkpoint spikes, but, well, they can be still troublesome. Like write-ahead log should be written quite good. That have some limitations on copy and write file system sometimes. And, well, pretty much every point of this I/O stack should be optimized for that exactly type of workload. Then we put loads of dirty pages down to the disks. What generates most of I/O problems in Postgres? As I said, this page synchronization, when we need to write a lot. Besides of this, auto vacuum can be sometimes troublesome, but, well, it depends of exactly how your workload works. Sometimes cache refill can be bad, but, well, today many of you, I'm sure, are using SSD disks, which is much better. And sometimes you can have lots of problems with normal Postgres workers with their I/O. But this is out of scope of this talk, and basically I can say then your ordinary PostgreSQL processes performing some I/O operations, that's generally bad, and you need to avoid that. Like those processes are not designed to make checkpoints, for example. If they trying to dump the dirty pages to the disk, that means that actually something is quite wrong in your database setup. That's an emergency measure. It's not like normal process. So for a long time, for databases, the huge problem was how to maximize the throughput. This word throughput was quite common for all talks about database performance in terms of I/O. And well, when you're talking about throughput from the user space, from database to the disks, every part of this stack could be involved. And most likely we are talking about throughput because this part of the stack was quite vulnerable. The disk was slow. So because the disk was quite slow, a lot of efforts and time of developers of Linux, kernel of Postgres were actually concentrated around how to maximize throughput in the rest of this stack, because latency of the disk was quite high. We need to move the heads on the disk and so on, which could not be improved. And most people are looking on these, not on these. But technology actually don't stay in one place, and some evolution actually goes on, and the situation change. Why I actually concentrate on throughput and latency? If we have like so complicated I/O stack, it's actually sometimes easier to maximize throughput, like using parallelism where we can. The typical example of this, not correctly parallelism, but some helper process was like, then PostgreSQL checkpointer cannot manage the checkpoint, the dumping of all those dirty pages. PostgreSQL people came up and invented the background writer. So between checkpoints, we can use background writer to help checkpointer. That's a typical example of maximizing throughput, because we could not minimize latency anymore. Because, yeah, minimizing latency is quite tricky. But now the situation changed, and now we have SSDs, which probably do not make the DBA job obsolete, but they can actually reduce this latency component in the I/O stack. And the whole system needs to be adopted for this modern situation. So, because of high latency of rotating disk, that's some historical part, there was lots of effort how to improve the performance of this stack in terms of throughput. And you know probably all these recipes, like you need to tune VM, dirty ratio, and those things. That was the times of rotating disks, as well as battery-backed cache and things like this. This is like the DBA task to tune those parameters and so on. But inside the Linux kernel, there are lots of internal optimizations like that. We're using SSDs, but the methods inside the Linux kernel are designed to move the heads on the disk efficiently. But SSD has no heads, basically, and it is a much more parallel-aware thing compared to even disk array. So this is an I/O stack. We can use direct I/O, we can use page cache. In terms of Postgres, we use page cache, but we need to go through all this stack. Well, file system, that's nothing interesting here probably, but there are lots of benchmarks about this. There are several approaches how to improve file system performance. For example, do not use write barrier on X4, but we actually look deeper into the kernel. In the kernel, there is a so-called bio layer, or block input-output layer. And the task of this part of the kernel is actually to form input-output request. So this is basically bio, it's a C structure. And we take those blocks like in database practically. And we form some vector of those blocks to put it finally to the disk. The interesting thing here is that we operate pages inside our database and in user space. And on the disk, on the old disk, we're operating with cylinders, sectors, and those rotating things heritage, which was quite obvious when people were programming those SD driver, SCSI, and so on. And this part of the Linux IO stack was specially designed to make some smooth and efficient transition from the pages to the cylinders, sectors, and those old school things with rotating disks. Then we actually form the request which goes for IO and instructs driver, like put this piece of data there and so on. We can optimize the input and output in some way. And basically, for a long time, all this optimization was about where we store this data. If we can just dump this data to the disk using single movement of the disk head, that's efficient. So all the optimization here was based to like merge and sort these vectors of blocks to fit to the disk, if they, for example, can be stored together. And that's why emerged this idea to have an elevator or IO scheduler, which can actually help with sorting of all those pages and putting them to the disk in most efficient manner. Before the kernel 2.6, quite old time, there was just a single elevator, so-called Linus elevator. And well, it was like many things which Linus made himself, consider it as a perfect thing, very simple and very good working. But in effect, nobody just cares if it works. So it's just, it does something. If it does that efficient, nobody knows. We have disk latency, and well, to optimize disk latency, it's difficult, physical limitation, so we just use something. And this type of elevator had lots of problems, mostly because it doesn't fit the job even for rotating disks. But for modern disks, that simply wouldn't work. Starvation, then you write some information, you need to read information from another part of the disk, etc., etc. So lots of problems. Between kernel 2.6 and early versions of third kernel, some people come up and invented some different schedulers. But actually inside the logic of those schedulers, there's still pretty much some improvements over the old Linus elevator. The first of them, more universal and more typical, was like complete fair queuing. The idea behind this type of elevator is like you have processes, and for each process you provide input-output queue, which basically provides fair access to input-output. But when we have Postgres, just imagine how efficient it would be. For example, you have some connection to the database, and you have some percent of I/O. When we have auto-vacuum process, it basically have the same access to the I/O. Then we have checkpointer, and it has the same access to the I/O. This is pretty much not very efficient because for checkpointer we need a lot of I/O. For a normal PostgreSQL process which performs some select, we probably do not need any I/O at all. Maybe it just takes the data from the cache or just handles the connection of the DBA, which is idle. So we don't know. So for a specific workload like database, this scheduler was always not that universal, not that good. Maybe for a desktop environment it was better. Then emerged the deadline scheduler. Deadline scheduler was like some sort of improving the idea for improving the situation. Basically, it has two types of queues, like queue for reading, queue for writing. And it just starts to read or to write, but all the requests are actually tagged with timestamp. And that timestamp allows kernel to figure out if this request timeouted or not. And if it is timeouted, like we have huge amount of information to write, it takes long time, we hit the timeout, then the kernel changes the priority of this queue. So basically, if we have a lot of input-output, finally it would rise in priority and work more efficiently. It did. It actually, for rotating disk with normal rate controllers, it was much better than CFQ. But still not perfect, and well, especially not perfect for SSDs. And some people come up with idea of no-op or non-scheduler for devices which allows much more parallel execution of I/O. Like disk arrays, SSDs, the main difference is like they allows much more parallelism. And this idea was like basically this scheduler doesn't change anything. It doesn't perform merging, sorting, things like that. It just do nothing. So it's like a placeholder for a scheduler. And it turns out it was much more efficient for high parallel storages in comparing to other two. And probably at that point or slightly earlier, many people started to work on real improvements of I/O stack. And now we actually hit some terminology problems. Because as you remember on that diagram with stack, there was I/O scheduler which was some part of the kernel working with request layer. There's lots of discussions if we need to improve this, but finally Linux developers came up with idea that we need substitute practically a lot of these. So basically not only substitute the whole request layer and add some elevator here, but adopt the device driver to work with a new analog of request layer and probably change many things here. So after the new approach emerged, we practically have a new input-output stack. Part of this is NVMe or non-volatile memory driver, and part of this is so-called bulk MQ, which is the scheduler and the request layer simultaneously. And now it actually has some new schedulers inside. Because of effectiveness of this no-op, the idea was we need the I/O scheduling which is initially designed to support lots of parallelism. First, this thing was introduced in 3.13, and I think the latest version was merged into the kernel 4.10 together with NVMe. So before that it was not that efficient, but you can probably run into it and probably use that together with late third kernels if you use NVMe, because NVMe it says that it's NOP, but basically in late third kernels it was NVMe, in spite of what you can see in your graph or whatever. So the idea is that SCSI is not parallel, and you cannot scale your input-output requests. So basically, if from user space, Postgres with fsync in checkpointer, you initiate the write request, it goes straight to the disk driver, whatever you have beneath. And this is a problem, basically, because you issue input-output request, it doesn't scale. It basically goes through the hardware. How to improve those things? The old approach to elevators was like, we have a CPU, a queue, and the disk, and that's just straightforward. So we basically go through, and if we are busy, we are busy. Then at some point, there were some special queues for single process, for example, which tends to be slightly more effective, but still not. The game change for bulk MQ approach was that it basically parallelized this queuing. And now in Linux, we have, for example, CPU on NUMA node, which has each its special software query. And through this software queue, you can actually put a lot of input-output. And in this software queue, you can do any optimization, like tagging for specific processes or for specific virtual machine, like sorting, merging, things like that, which tends to improve the performance of input and output. And then all of those things are ended up in queues on the hardware. And in case if we have an SSD, we usually have more than one hardware queue. And this is much more efficient. So basically we got the parallelism on the level of request layer. That's why it's substitution of request layer, not the just scheduler which works aside. So basically, then we rebuilt the this part of the stack. People start to think that we actually need another scheduler. But the scheduler which can be aware of modern SSDs. Currently, there are two major schedulers for bulk MQ and VME aware kernels, newer kernels. One of them, which is more complicated, and some people tend to compare it to CFQ, is BFQ, or budget for queuing. The idea is it has some math behind which allows to figure out that we have this input and output budget for this application for this device. And based on this budget, it actually increase or decrease the priority for this input-output. I wouldn't say it's quite efficient from my observation, so it's complicated, but well, it works. The Kibber is a different approach. It's just like a very simple scheduler which tries not to mess up with lots of mathematics around here with merge and sorting and things like that. Whichever you prefer, I have actually no recommendation right now because it's a relatively new thing. I would say that actually use the default with your current modern Linux kernel. Most likely it would work better. So from my experience, there is no such drastic changes comparing to like if you use deadline or NOP on SSDs. So basically not that important. After that, we have NVMe driver, and then sometimes we have improved parallel SCSI driver for that. There is a good upgradable, which maintainers keep current diagram of Linux input-output stack. You can take a look and figure out much more details than I can put on the slide. It's basically not that up-to-date about bulkmq, but well, actually, it's up-to-date like for 2 years ago or 1 year ago. So basically, it's fresh enough to figure out what is going on. And I hope the guys will update that soon. What is actually NVMe? NVMe, it's not just a driver, it's a set of standards for input-output drivers, which is quite good currently, and well, we all appreciate that finally major producers did that. For Linux, it's just a driver and set of standards how other parts of the stack interact with IO scheduler. For industry now, it's actually the new standard which is under construction. So basically, we have only NVMe currently working in stable for local disk. If we put something into PCIe, that works perfectly well, fast, and so on. But there are lots of work to make this real for fiber channel, for disk arrays, and that's really the future because that part needs lots of parallelism too. So currently industry works in that direction and results are quite good. So stable now is version 3 of this standard, and the already pre-production version 5 can basically allows more than 32 gigs per second for one channel of fiber which connects you to the disk array. So it's very impressive disk performance, I would say. But the next problem is, like with that latency change, are the database actually aware of that development? And is it okay just to put the database on this extra fast storage? Would it use that good? I would say that's actually a difficult question, and we still, for example, in Postgres have no real parallelism in bulk input-output operations. So basically, we have a checkpointer, which is not quite parallel, and we have a background writer, which is non-parallel. And that's it. So basically, the improvement of current storages are all based on high parallelism in storage. And well, the database cannot handle this. So probably it should be a lot of things improved before we can actually benefit. But well, if you move from no-op to modern kernel with bulkmq, I saw the performance improvements like 4 times. So it can be actually quite good for you, but I'm not sure because I don't know your workload. So well, situation could be improved, maybe not so drastically like excited developers on NVMe reporting. What's the latest things in NVMe and bulkmq during the development cycle of kernel version 4? The first thing was IO polling. That's an interesting example. For a long time, the idea was like if you form an input-output request, you send it to the disk, and then disk driver takes care about the results. So you have an IRQ, and you handle it, then the operation of IO ended, and then you return to the kernel to the user space, and so on. For low latency disk, this is actually not very optimal because you need to wait for the interrupt, and that's a long time. Probably your operation will end up sooner, and you will have a huge overhead. Immediately come up the idea of polling. So basically, then you send the write request through the stack to the disk. You can constantly poll your device and figure out if it finished or not. And because SSDs are quite fast, we run into another problem. On this polling, you can actually spend lots of CPU resources. And your CPU is busy, and, well, your database is not happy. So after the first naive approach, the so-called hybrid polling was introduced. So basically, current idea is that you send the write request, and at some point you poll the device and try and figure out if it finished. Then you sleep for a while, and then you actually poll again, and most likely it would be much more efficient than wait for interrupt. So that was a huge improvement of performance of BulkMQ and NVMe together. There are no new schedulers like BFQ Kuber for 4.10 or 4.12. Here I think 4.12 is much more correct. IO-tagging was introduced, so basically you can move the request from one queue or to another queue, and based on those tags you can manage the priorities of input-output. That was specifically good for virtual machines, but I think actually for databases it can be also quite useful because different processes have different I/O profile. And besides of that, there are some direct I/O improvements in the NVMe connected to the internal optimizations of SSDs. And a final small note on the direct I/O, because we're talking about databases. We are at PostgreSQL Dev Room, and well, that's a question people constantly ask. What is the current situation with direct I/O in Postgres, and why not just grab all the source and open every file with direct? It's simple. Why you don't do this? So currently, PostgreSQL doesn't support direct I/O for anything useful in production. I would put that in that wet way. So we basically can use direct I/O for write and write ahead log. But here's the problem and explanation why Postgres do not use that for something useful. If you open the file with direct, you need to work with this file exceptionally with direct. Because if you open the file with direct and then, I don't know, archive command or something like pgdump or something like this, handles this file without direct, you will have problems. Most likely some crash or something like this. If Postgres works just like a standalone database, that's okay to write ahead log with direct. But if you enable replication, you probably will have an archive command, which is in Postgres can be like just bash script or something completely unaware of how you open the file. And well, you will run into the problems, and because of that, Postgres automatically switch to buffered I/O for write ahead log, even if you try to use direct I/O in this case. The main problem from my point of view is that direct I/O is a very Linux specific thing, and you need to invest lots of efforts to introduce and maintain platform dependent code. So basically, even if PostgreSQL community will agree to do this, that would be like not easy task because you need to write lots of code specifically for Linux. And generally, PostgreSQL community is not quite easy about bringing into the project very OS-specific things. Generally, Direct.io maybe is the best solution we have now, in spite of many people talking that it's not quite good in terms of implementation and so on. But, well, I think finally Postgres will move towards this direction because now it's like basically the only classical database which doesn't use that. I don't know, actually, it actually is a good idea if we try to figure out if Linux version of MS SQL Server uses that. But well, the only exception is MS SQL Server for Windows, yeah, because they do not have Direct.io. MySQL uses, Oracle uses, DB2 uses. So that's all about Direct.io and all about the recent changes in Linux stack. And if you have questions, it's time to ask them. Thank you. Yeah. Question? Yeah.
In your talk, you described only like bare metal implementations of PostgreSQL, which means like private cloud where you can negotiate certain things with a provider, and the public cloud has has those things inside of it, but handled totally in a different way.
Well, I would say that most likely they all have the same things inside. Because even if you deal with the public cloud, they have serious problems with improving performance. And I don't believe they do not use this achievement of Linux kernel. But with public cloud, basically you can never be sure what exactly they do. And that's a part of the game.
But but it stops being a PostgreSQL problem. It becomes a question of choosing the flavor.
I still believe that many people use private cloud or bare metal installation, actually. And for them, it's a problem. We're not talking about maybe private clouds here, but for public clouds here, but for private clouds, it's still a problem. You need to tune your Linux, you need to figure out what's going on. So basically, many of those improvements were actually introduced for private clouds.
So a little bit on that. So the thing is, you're provided with Virtual BLK device. In case you're lucky, you might negotiate Virtual BLK with multi-queue support. Yeah. But it's still different from what you described because Virtual BLK device is not SSD or HDD or NVMe. It's as a thing on its own.
Yeah, well, I would say that the idea of how to improve performance of Postgres on virtual I/O, on any virtual I/O, it's quite different problem. Because, for example, here we're talking about the lacking of parallelism in the Linux kernel infrastructure to handle SSDs. That's one problem. But if we talk about virtualization, for example, immediately emerged the problem of unstable latency, which is quite different story and, well, it's outside the scope of this talk. It's also the problem and quite serious problem, but, well, it's a different story. Yeah. Yeah.
Thanks. Thanks for the talk. Have you seen much demand or traction for open channel SSDs? And if so, like how far out do you think that might be?
Well, I would say I have heard about that because I was interested in the topic. But regret to say, I do not see that much in production because, well, my primary job, I'm working for the customers, and then the customers running databases, they tend to buy good SSDs and use vendor-specific things for them. It's just real life. So I will quite appreciate to have some feedback if someone uses, and, well, I will take a look at it. Yeah.
Any other questions, please?
Just in your last slide, you have atomic flag. May you give
What?
some details about atomic? Any details about?
Well, some SSDs have another option, or atomic, which is quite useful for writes. But the problem is you cannot use OAtomic without ODirect. So basically you need to use ODirect to benefit from such low-level optimization for SSDs.
But will you support it for any block size? 16K, 64K, or only 4K?
I don't know, to be honest. Because, well, Postgres doesn't support that. I don't know.
And what is the smallest block for DirectIO? Acceptable? Because you speak about blocks, but you have file system, right? So even you write 1 byte, it will be still 4K today.
Well, Postgres operates 8K if you don't recompile it. So basically, I/O can bring benefits on that block size. And basically, I believe it also will bring lots of benefits on larger sizes of the blocks. Because, well, the whole mechanism was introduced partially for databases, and many analytic databases tend to have a larger block size.
Okay, and any plans then we don't need to call fsync when you use DirectIO? Because right now
It's a different story. It doesn't depend. Basically, Postgres heavily relies on fsync. I don't know if you probably visit Tomasz talk yesterday, yeah, I believe, yeah, about fsync problems. You will see that basically all mechanism is about fsync. So basically, it's like POSIX standard as we understand that, and anyway, you need to issue fsync.
But why? If you're already on ODirect, so 20 years ago Solaris used ODirect without fsync. So why Linux still you need fsync?
It's a good question, actually. Yeah, probably we have several right persons to answer that low-level question.
Yeah, the reason is that there is a development cost of implementing direct I/O on all operating systems. So we don't have the manpower to do it yet. We may next year or the year after that, but that's the only reason.
Thanks, Elvira.
Any other questions, please? So, thank you, Ilya.
Thank you.